Oxymercuration-demercuration is an alkene addition reaction. So I'm going to illustrate the reaction with this very simple alkene. This reaction is a two-step process. Not two steps in the same way that SN1 and E1 are two steps, but this is two individual reactions that take place in sequence. The first step is the oxymercuration step. And in that first step, we react our alkene with a compound called mercury acetate, HgOAc2. And this mercury acetate is in a solvent. One possible solvent is water. And right now, at this particular point, we will only be looking at oxymercuration-demercuration reactions where water is the solvent. But later we will look at some examples where we change this solvent up. Let's talk a little bit, before we move on, let's talk a little bit about the mercury acetate, HgOAc2. OAc is our shorthand for acetate, which is an ion that you became familiar with in general chemistry. The acetate ion is the conjugate base of acetic acid, CH3COO-. So mercury acetate in water, in this first step, produces a product. I'm just going to call it product number 1. That particular product is not what we're trying to make in this reaction, and so it is reacted again. So this is going to be the step 2 part. It undergoes demercuration, and the reagent that we use there is called sodium borohydride, NaBH4. The product of this second step is the desired product of this reaction. This particular reaction is a hydration, so we are adding a water molecule to the carbon-carbon double bond. The water molecule is actually coming from right there, so let's actually make that water molecule a different color. Let's write it in a different color, and let's add that over here to our products. So this is the desired product of the oxymercuration-demercuration reaction. This product that is made in between the first and second step really isn't important to us. We don't draw it. We don't talk about what it might possibly be. Typically, when we write the oxymercuration-demercuration reaction, just write it like this, where we show the first arrow immediately followed by the second arrow, and then we only draw the final product of the reaction. The conditions of this reaction first of all, it is a Markovnikov reaction. So that helps us predict the correct placement of the hydrogen and the OH group that are being added to the double bond. The reaction undergoes no rearrangement. There is no carbocation intermediate formed in the mechanism for this reaction, which means that there's no possibility for rearrangement. So this reaction differs from the previous hydration reaction that we've looked at in this aspect, that rearrangement is not a possibility. Last but not least, if you form a chiral carbon in the oxymercuration-demercuration, your products will be a non-racemic mixture of enantiomers. We cannot predict which enantiomer will be major and which one will be minor. We know that we make both enantiomers, and we make them in a non-racemic ratio. So let's look at some examples of this reaction in action. Here is a slightly different way to indicate the two-step process for this reaction. So instead of writing the first arrow followed by the second arrow, we'll just write one single arrow, and then this means these are the reagents for step 1, And this means these are the reagents for step 2. And this is pretty common notation for a multi-step reaction. If you have multiple reagents in a step, for example, in step 1, we have 2 different reagents, we'll just separate those reagents from each other by a comma. So the way that we would verbalize this, the way that we would read this is step 1, mercury acetate and water. Step 2, sodium borohydride. Let's predict the products of this reaction. So first of all, we know that there will be no rearrangement, which means that our carbon skeleton is unchanged. We know that we are working on these 2 carbons right here. One of them will be getting a hydrogen and the other will be getting an OH coming from this water molecule right there. We're going to follow Markovnikov's rule, which means that we should understand how many hydrogens were originally on each carbon. This carbon had 0 hydrogens, this carbon had 1 hydrogen, which means that our new hydrogen from the water molecule will be added to this spot right there, and our OH group will go here. So this is the constitutional isomer version of the product. Now to finish this off, we should ask ourselves, for those 2 carbons that we worked on, did either one of them become chiral? This carbon has 2 hydrogens. 2 of the same things means it's achiral. This carbon, however, is chiral, has 1, 2, 3, 4 different things attached. So we have to communicate that we have made both the R and S version of this particular molecule. You get to choose how you would like to represent that. It's totally up to you. So I'm going to pick one bond to make into the dash bond, and I'm going to pick another bond to make into my wedge bond. And again, you're just making that choice yourself. Pick one to be a wedge, pick the other to be a dash, and then draw the enantiomer in whatever method you prefer to use for drawing enantiomers. So my preferred method for drawing enantiomers is to just simply convert the wedge to a dash and convert the dash to a wedge. So those are the 2 products for this reaction. Let's practice again with this one down here. So first of all, we know that we will make no changes at all to the carbon skeleton. So let's draw that out, and let's find the carbon atoms that we are working on in this molecule. So these are the 2 carbon atoms that are going to be changed. We are following Markovnikov's rule, so we need to figure out how many hydrogens started out on those 2 carbons. This carbon had 1, this carbon had 2. 2 hydrogens means that our new hydrogen from the water molecule, the new hydrogen will go right here. So let's add the hydrogens that we started with, and then we'll add our new hydrogen, and we will add our OH. Did we make any chiral carbons? This carbon has 1, 2, 3, 4 different things on it, so this carbon is chiral. This carbon has 3 identical things, so it is not chiral. Because this carbon is chiral, we need to show its stereochemistry. And again, we will pick whatever we want. Any bond, pick a bond, any bond, and make it a wedge. Pick a bond, any bond, and make it a dash. And then draw the enantiomer. And that's all there is to it.